We really want to get into circuits, and so this chapter has transitioned us into circuits. We've defined what a capacitor is based on where we've been, which is electrodynamics, and now we are truly into the circuit aspect. Our symbol for a capacitor is two parallel lines, which kind of looks like a parallel plate capacitor, and we designate that by C with the units of farads. We want to be able to simplify capacitor circuits, and one configuration that we might see are capacitors in parallel. We want to find an equivalent capacitance that represents capacitors in parallel. What we mean by parallel is that all of our devices are actually connected on both ends. So here we have a battery with a voltage connected on both ends to capacitance 2 and capacitor 1. And we want to find an equivalent for this parallel combination of capacitors. Now, if we truly find an equivalent, it should have no different effect on the battery than the original circuit. In other words, the same action of the battery will occur in our equivalent circuit as what happens in our original circuit. That must be our constraint. Now we'll note that since these are in parallel, things in parallel have the same voltage. And in this case, we're going to have the same voltage in either circuit. So it'll have the same voltage as our equivalent capacitance as well. So the voltage of our equivalent circuit will equal V1 will be equal to V2. They'll cross the same 2 points in the circuit. You'll go the same potential difference to go from that point to the lower point. They have the same voltage. Also, like I said, each battery should not know that we have a different circuit. It must be truly an equivalent circuit. So the same charge will leave the battery in either circuit. And so if we have charge coming out of this first circuit, it's going to split. Some of it's going to go to C1, some of it's going to go to C2. In our equivalent circuit, all the charge will go to our C equivalent. So we'll have Q equivalent is equal to Q1 plus Q2. They should be the same total charge. But we know from our definition of capacitance that Q is equal to CV. So we have C equivalent times V is equal to C1 V1 plus C2 V2. Now these voltages are all the same, so I can divide both sides of the equals by the same voltages, and I'm left with C equivalent is equal to C1 plus C2. What this means is capacitors in parallel add. We did this for 2 capacitors in parallel, but we could have done it for any number of capacitors in parallel. If we have a bunch of capacitors in parallel, we simply add them together, come up with the sum result, and that is our C equivalent. So capacitors add in parallel, kind of like, as we'll see very soon, resistors in series. Resistors in series add, capacitors in parallel add. What about a series combination of capacitors? Well, the charge has to be the same in all the plates. We'll show this in a moment here. Here's our circuit with a series combination. What I mean by series is that they're all on the same line of wire, so there's no other connections. Whatever passes through one has to pass through the other because there's only one path. So we have a series combination of C1 and C2. We want to find an equivalent circuit that represents that. Now out of the battery, we're going to have a positive Q come out and charge the left-hand side of C1, and negative Q come out and charge the right-hand side of C2. As they do that, they will induce an opposite charge on the other plate. And so I'll have a negative Q on the right-hand side of C1 and a positive Q on the left-hand side of C2. This is okay because this central wire was neutrally charged anyway, and so we still are neutrally charged. We just had a positive Q go one way and negative Q go the other way. But we can see with this configuration that both C1 and C2 have the same value of charge. Capacitors in series will have the same charge. And since our equivalent circuit is truly equivalent, the same charge that comes out of the battery in our first circuit should come out of the battery in our equivalent circuit. So it will have the same charge as well. So capacitors in series have the same charge, and they have the same charge as their equivalent capacitance. And that is going to be a rule that we're going to use quite effectively. So capacitors in series have the same charge. Q equivalent equal to Q1 is equal to Q2. Now if we had a series combination across this battery, we're going to have a potential drop across C1 and a potential drop across C2, and that should be equal to the full drop across C equivalent because they're across the same battery. So it should be true that V is equal to V1 plus V2. From our definition of capacitance, since C is equal to Q over V, V should equal Q over C. So we have Q equivalent over C equivalent is equal to Q1 over C1 plus Q2 over C2. But all these charges are the same, so we can divide both sides of the equals by the same amount, get rid of the charges, and we're left with 1 over C equivalent is equal to 1 over C1 plus 1 over C2. That is a formula that allows us to calculate the equivalent capacitance of a series combination. We did this for 2 capacitors in series, but we could have done this for any number of capacitors in series. 1 over C equivalent will equal 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 and so forth and so on. So if we had a bunch of capacitors, we could find the equivalent capacitance this way. Take the inverse of all those capacitors, add them together, and then take the inverse of that sum, and that would be our equivalent capacitance. This formula, as we'll find out, is exactly the same mathematical type of formula as what we'll use for resistors in parallel. So capacitors and resistors have the same kinds of formulas, but the reverse for the situations. Capacitors in series have a formula similar to resistors in parallel, and resistors in series have a similar formula to capacitors in parallel. So they kind of crisscross as far as their function. If we had a case where we only had 2 capacitors in series, it should be true that 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Let's find a common denominator for these 2 fractions. We're going to multiply them each by 1 to get a common denominator. And now I have 1 over C equivalent is equal to C1 plus C2 over C1 times C2. I can algebraically solve for C equivalent or just flip both sides of the equals. Mathematical technique. And we have C equivalent is equal to C1 times C2 over C1 plus C2. In other words, our equivalent capacitance for a series combination of 2 is equal to the product over the sum. I can do this for 2 capacitors in series, but you can't do it for 3. So it's not true that if you had 3 in series, it would be C1, C2, C3 over C1 plus C2 plus C3. That doesn't work. You can verify the math for yourself. So it only works for 2 capacitors in series. But if you had a bunch of capacitors in series, you could break them down 2 by 2 by 2 by 2. So for every 2, do product over the sum, break it down to 1. Next 2, do product over the sum, and start reducing your circuit that way, always taking them 2 down to 1 in successive order. That would work. And that's one way that you could simplify a capacitor network. In the special case, if I had a series combination of n equal capacitors, all of them the same, so I have 1 over C equivalents 1 over C plus 1 over C plus 1 over C plus 1 over C n times, then I would have 1 over C equivalents equal to n times 1 over C. Flip both sides of this equation, and we have C equivalents equal to C divided by n. N being the number of capacitors that we have equal in series. For instance, if I had 5 2 microfarad capacitors in series, the equivalent capacitance of that would be 2 divided by 5, or 0.4 microfarads. You say, well, how often are we going to get a combination of equal capacitors in series? It actually comes up a lot more often than you might think. So this could be a nice little formula to have handy for that case. Alright, so we want to simplify a capacitor network, and it looks like this. It's our first day on the job. We're electrical engineers, and we want to earn our pay. So we look at this and we want to simplify this. As we look at it, there's nothing in particular that is in series in this circuit. To be in series, you must be on the same line with nothing else connecting, so that the same charge and current must flow through one as it flows through the other. That's not possible right now as we see it, but we do have parallel combinations. We have a 1 in parallel with 3 and a 2 in parallel with the 6. So if we add those parallel combinations, because capacitors in parallel add, then we can simplify the circuit that way. So the 1 plus 3 is 4, and the 2 plus 6 is 8, and now we have this circuit. Now we have a 4 and a 4 that are in series, and we have an 8 and an 8 that are in series as well. For the series combination of 2, we can do product over the sum. So for the 4 and 4 in series, we could do 4 times 4, 16 over 4 plus 4, 8, which is 16 divided by 8, or 2. And for the series combination of the 8 and 8, we could do 8 times 8, 64 over 8 plus 8, 16, which is 4. So we would get a 2 and a 4. Or since they were equal, we could have done C divided by N. So it would have been 4 divided by 2 and 8 divided by 2, giving us 2 and 4 respectively. So now our circuit looks like this. And the 2 and the 4 are connected end to end, so they are indeed in parallel. So we can add them together, and our result is that the equivalent capacitance of this whole network is 6, whatever the units were, 6. If this were my first day on the job, I could say, well, let's just go in with some wire cutters, cut out the 6 in this original circuit, leave all the other components for something that we might want to use later, and then just redesign this network between A and B with just the 6 microfarad capacitor or whatever it is, and save my company some money, and they can pay my first hour on the job. So here are some key features of capacitor circuits. We want to use these series and parallel formulas to find C equivalent. For any particular individual capacitance, it must be true that Q equals CV. We're going to use this a lot. This will relate the charge on a capacitor to the voltage across a capacitor. Q equals CV. Capacitors in series have the same charge, and they have the same charge as their equivalent capacitance. This is very useful. So Q equivalent will equal Q1 equal Q2 if they're in series. Capacitors in parallel have the same voltage as anything in parallel, and they have the same voltage as their equivalent capacitance. So if we have a voltage combination, or a parallel combination, the voltage will be equal across all those branches of the combination. That's only for parallel. These are all very simple objectives, but they're actually what we're going to be using to analyze circuits. And if we know when to use them, then it will allow us to proceed in a very logical way in our circuit analysis. Let's try it out. Here's a problem. Determine the equivalent capacitance for the network shown. We have a 3 and 6 in series on top. Nothing else that we can do. There's nothing in parallel yet, because the 2 is not in parallel. The 2 is in parallel with the whole 3-6 series combination. So we're going to do product over the sum for the series, 3 times 6 over 3 plus 6, 18 divided by 9. 2 microfarads for our equivalent capacitance for the series combination. So we're left with a 2 and a 2 microfarads. So they are in parallel because they're connected end to end. So 2 plus 2 is 4. And our equivalent capacitance of this network is 4 microfarads. If we then connected this network to a 12-volt battery, calculate the charge on each capacitor. Well, the voltage across the parallel legs is going to be equal to that 12-volt battery. So we're going to have 12 volts across this 2 microfarads here, and 12 volts across the series combination of the 3 and the 6, which had an equivalent capacitance of 2. So the charge on our branches should be equal to the equivalent capacitance of each branch multiplied by the voltage across the branch. So Q equals CV. That's going to be 2 microfarads times 12 volts, or 24 microcoulombs. Note that we pass the micro all the way through. 2 microfarads will end up giving us microcoulombs. And that will be the charge on both branches, including the equivalent 2 microfarad capacitance up top. But we know that things in series have the same charge, and they have the same charge as their equivalent device. So the series combination of the 3 and the 6 will have the same charge as their equivalent 2 microfarad capacitance. Hence, the 3 and the 6 have the same charge of 24 microcoulombs. And so does the 2 down below. So by coincidence, all 3 of these capacitors have the same charge. Calculate the voltage on each capacitor. Well, the fortunate thing, since Q equals CV, if you know the charge on one capacitor, then you can calculate its voltage by that simple relationship. So, since Q equals CV, V will equal Q divided by C. So on the 3 microfarad capacitor, there'll be 24 microcoulombs over 3 microfarads. The micros cancel out, and you'll have 8 volts. For the 6 microfarad capacitor, it'll be 24 microcoulombs over 6 microfarads. Micros cancel out again, 4 volts. So the 12 volts is being shared kind of inversely. The 3 microfarads will have 8 volts. The 6 microfarads will have 4 volts. And the 2 microfarads will have 12 volts across it as expected. The whole branch is in parallel with the battery. Energy stored in a capacitor. The energy stored, the potential energy stored in a capacitor is equal to 1/2 its charge times its voltage. But since Q is equal to CV, we can rewrite this as the energy stored is equal to 1/2 CV times V, or 1/2 CV squared. And since V is equal to Q divided by C, we can also rewrite this as 1/2 Q squared divided by C. Any one of these 3 forms is valid for calculating the energy stored in a capacitor. It involves the variables charge, voltage, or capacitance. So if you knew 2 of the 3, charge, voltage, or the value of the capacitance, you could find the energy stored in that capacitor by using one of these 3 formulas. The most useful ones are either the 1/2 CV squared or 1/2 Q squared over C, because most of the time you're going to know the value of the capacitor in question. And then, so you just need to know the charge or the voltage on it, voltage across it or the charge on it, so that you can calculate the energy stored. Neat little formulas. Let's put it to work. The energy stored in a 12 microfarad capacitor is 130 microjoules. Determine the charge on the capacitor and the potential difference across it. Well, we know the capacitance and we know its energy, so we can solve for the charge. We know that The energy stored is 1/2 charge squared over capacitance. Rearrange this, multiply both sides by 2c, and take the square root. So Q will equal the square root of 2c times the energy U. 2 times 12 microfarads times 130 microjoules. The micros, 10 to the minus 6, actually will come out of the square root. And we'll have 55.9 microcoulombs for the charge. We could also rearrange this, knowing the capacitance and the energy, by the second equation to find the voltage. Multiply both sides by 2, divide by C, take the square root. So the voltage is 2U over C. Micros cancel out, 130 microjoules over 12 microfarads, and we're going to have the square root of that is 4.65 volts. Let's try another circuit. For the system of capacitors shown, find the equivalent capacitance of the system. We're looking at this. There's nothing in particular, no two devices in parallel, but we have this series combination of the 3 and 6 and a series combination of the 2 and 4. And there's only 2 of them, so we can do product over the sum. For the 2 and 4, it's going to be 2 times 4 over 2 plus 4. 8 divided by 6, or 1.33 microfarads. And for the 3 and 6, 3 times 6 over 3 plus 6. 18 divided by 9, or 2. And so as we replace those, then they would be in parallel. And now we have a 1.33 plus a 2, and that gives us 3.33 microfarads for the equivalent capacitance of that network. Find the charge across each capacitor. We know the voltage across the whole thing, 90 volts, and hence we could find the charge on the each branch, actually, because that's the same voltage. The voltage is in parallel with each branch, the 3 and the 6 and the 2 and the 4. And the equivalent capacitance of each will have that 90 volts across it. So for the 2-4 branch, our charge on the equivalent capacitance of that branch will be 1.33 microfarads times 90 volts, which will give us 1.2 times 10 to the minus 4 coulombs. Now, since things in series have the same charge as their equivalent capacitance, this will be the same charge that's on the 2 microfarads and the 4 microfarads. For the 3 and 6, we'll take the 90 volts across the equivalent capacitance of that series combination, which was 2 microfarads. So we have 2 times 10 minus 6 times 90 volts, give us a charge on the equivalent capacitance of that branch, 1.8 times 10 minus 4 coulombs, and that also will be the charge on the 3 and the 6, because things in series have the same charge as their equivalent device. So we now know the charge on all 4 capacitors. Let's find the potential difference across each capacitor. Well, we know Q equals CV, so V should equal Q divided by C. So the voltage on the 2 microfarad will be its charge divided by its capacitance. 1.2 times 10 minus 4 coulombs over 2 times 10 minus 6 farads will give us 60 volts. For the 4 microfarads, its charge over its capacitance. 1.2 times 10 minus 4 over 4 times 10 minus 6, 30 volts. So 90 volts is shared, skewed again. 60 volts across the 2 microfarads, 30 volts across the 4 microfarads. For the 3 microfarads, its charge over its capacitance. 1.8 times 10 minus 4 coulombs over 3 microfarads, 60 volts. And for the 6 microfarads, its charge, 1.8 times 10 minus 4 coulombs, same charge, over its capacitance, 6 times 10 minus 6 farads, 30 volts. So those are the voltages across each capacitor. What's the total energy stored by the whole group? Well, we know their voltages and we know their charges, so we could use either one. The the energy stored in the 2 microfarad is its charge squared over 2 times its capacitance, and that gives us 3.6 millijoules. For the 4 microfarads, its charge, 1.2 times 10 minus 4 over 2 times squared over 2 times its capacitance, 4 microfarads, 1.8 millijoules. Q squared over 2C for 3 microfarads gives us 5.4 millijoules. Q squared over 2C for the 6 microfarads gives us 2.7 millijoules. So those are the energy stored in each capacitor. So the total energy stored in this circuit is 3.6 plus 5.4 plus 1.8 plus 2.7 millijoules, or 13.5 millijoules. Note that our equivalent circuit should be no different than our original circuit. In other words, if we had an equivalent circuit there, it should also store the same amount of energy. If we use the equivalent circuit, 1/2 our C equivalent times the voltage, which is the full voltage across it squared, which was 1/2 3.33 microfarads times 90 volts squared. Yes, we get 13.5 millijoules for that. So it wouldn't matter. In fact, that would have been easier if we had gone straight for the equivalent circuit, found the energy stored in that, and that would be the total energy stored in the whole circuit. These are the techniques we wish to use on these capacitor formulas. It's logical, it's straightforward, it's refreshing to have this kind of thing going for us, the mathematics. So try your hand at the problems in chapter 26, and if you get stuck, take a look at the videos on EduCreate.